Okay, so now let's take a look at how the solution process, how the dissolving process of a solute in a solvent happens in the first place. And we can think of as just a very simple example. If we were to zoom into a similar example we looked at before. So for instance, if I have a beaker and it's filled with some water, and then I had to take some sodium chloride and I add it to this, right? So this is my NaCl. Now, if I were to zoom in on my NaCl, we know that it's a solid, and it's going to be made up of Na plus and Cl minus that are packed really close to each other, right? That's what makes it a solid. That's the crystalline lattice, repeating pattern of positive and negative all the way throughout this thing. So in order for the sodium chloride to dissolve in the water, what actually has to happen is these ions must separate, first of all, from each other. So then that would entail separating these or breaking these very strong attractive forces between the positive and negative. So now we're going to have sodium ion, chloride ion, sodium ion, chloride ion, etc. And then what also has to happen is the water molecules have to separate from each other as well. So the water molecules are separating from each other. The water molecules aren't breaking down; they're just separating from. So we have your water is made up of, it looks like this. The particles can zip around, not zip around. They can move. They can slide past each other fairly easily. So these now need to be separated, and then the last thing that has to happen is the ions then need to be surrounded by the H2O molecules. Okay, so if we were to color code these, let's say your water molecules are in orange here. Okay, then when we separate them, right, what has to happen is that these need to come in and they then need to surround each of these ions and keep them separated. Because if you don't keep them separated, they're just going to combine again, right? Positive attracting negative, and it's going to form back the solid. So there are three things that need to happen. The solute particles must separate, the solvent particles must separate, and then the solvent needs to surround the solute particles. And that process is known as solvation. So solvation is where the solvent surrounds the solute particles, right? And it keeps the solute particles from recombining. When the solvent is water, we give it a special term. We call it, instead of solvation, we say specifically now, it is hydration, right? So in the case of the example above, right, yes, this sodium chloride, they're being solvated by water molecules. We can also say that the sodium chloride ions are being hydrated, right? Because water is a solvent in this case. So we have three types of interactions that we need to consider. We have these solute-solute interactions and solvent-solvent interactions that need to be broken. Okay, and we need to break those interactions. This will require energy. In other words, it is endothermic. And then when we form these solute to solvent interactions, when the solute now get attracted to the solvent, right, this needs to be formed. And then, as you can imagine, this is going to release energy, which means this is going to be exothermic. Okay, so we have an interplay of breaking interactions in the first two, the solute-solute, solvent-solvent interactions, and then forming interactions or forming attractions between the solute and the solvent. So these solute-solute, solvent-solvent interactions, these are the things we talked about before, right? When we looked at intermolecular forces of attractions, we looked at dispersion forces, we looked at dipole-dipole forces, we looked at hydrogen bonding. Okay, then we also we can throw in there our ionic attractions, right? Positive attracting negative, right? We talked about all of these, and that's what you're going to find in the solute-solute, solvent-solvent interactions, right? Those are the forces that keep the solutes together, that keep the solvent together. We need to break these to separate the solid particles. You need to break them to separate the solvent particles. And then we're going to form these solute to solvent interactions. Now we have, right, two different pure substances. We are now going to look at some new types of interactions, such as we can have things like ion dipole interactions that form, right? So here we have a dipole that we find in something like water. So if I have my H2O, right? We know that we have oxygen in between two hydrogens. So if I have, and we know the oxygen is slightly negative, the H is slightly positive. So if I have a sodium ion floating around, it would make sense then that the negative, slightly negative O, right, would be attracted to the slightly positive, not the slightly, but the very positive sodium ion. And then conversely, the slightly positive H's would probably be attracted to the negative chloride ions, right? These are ion to dipole interactions. We can have dipoles that are induced by other dipoles. So for example, carbon dioxide, which is normally a nonpolar molecule, it can a dipole can be induced in it by the dipole that is already in water, right? So here the water, which is polar, we should know that what induces or causes. Induces is another name for causes a dipole to form in another molecule or another particle. And as a result, those two things can be attracted because now you have dipole-dipole interactions that result. We can also have dipoles that are induced or caused by ions, right? So in the case of oxygen, O2, okay, non-polar because both of these have the same electronegativities. However, if we have an iron ion, like a Fe2 plus that has a charge on it, this can actually cause or induce a dipole in the non-polar molecule. And as a result, those two things can be attracted to each other. So when we have solutions being formed, we have two different things at least, right? A solute and a solvent. We have these new types of intermolecular forces that we need to consider, and those are the forces that will then keep the solute and the solvent close to each other and keep the solution intact. So if we were to chart or to plot the energy changes that accompany the solution process, we can actually see that it's a three-step process that's occurring. So our starting point is down here in the bottom left. So I have my my solute particles, right? So let's say it's a solid. Particles are packed very close together, right? We have your intermolecular forces of attraction. In this case, it might be ionic interactions. We have our solvent here, again, pure solvent, intermolecular forces of attraction. We first of all need to separate the solute, okay, particles from each other. So that is going to cost energy or requires energy, as we talked about before. So we have now separated solute particles. We also need to separate the solvent that is also going to require energy. So that's the second step up here, actually. So that requires energy as well. So now we have our separated solute, separated solvent. Now these two can be attracted to each other via those forces we talked about before, right? So as they're attracted to each other, as attractions form, that process then is what the solution process is. The particles get solvated, so we have solvation happening here. As the solute particles become surrounded by the solvent, and that process then is going to be exothermic. It releases energy, right? Which is why we're going in this direction now. So delta H here is less than 0. And then we end up with our solution at this point. Right, so if you take a step back and look at it, this kind of looks like Hess's law and the Born-Haber cycle. There are lots of parallels we can draw where the solution process, the delta H of the solution going from the separated solute, the separate solute, the separate solvent into the solution, so that delta H of the solution, enthalpy change of the solution, is simply the sum of step 1, step 2, and step 3. Right? So to get from the separated solute and the solvent from here to the solution, right? This pathway in yellow, it's the same as going from this first step, then the second step, and then the third. We end up at the same point. So again, it's a state function, as we know delta H is. So the delta H of the solution then would be delta H 1, step 1, plus delta H, step 2, plus delta H, plus step 3. So if we know what those delta H's are, we could actually calculate the delta H of that solution. So in this particular example, the delta H for this solution here, right, is greater than 0. So we can then conclude that this is an endothermic process. For this example, could also be exothermic, depending on how much energy is released when the solvation process occurs. Okay, so delta H of the solution can be exo or endothermic. Okay, if it were exothermic, the solution where we would end up would actually be somewhere down here of the solution. Okay, but in this case, the example that we did before, the delta H of the solution, actually not the delta H of the solution, but the solution was actually higher than the energy of the solution was higher than the energy of the individual solute and the individual solvent. So depending on the magnitude of the delta H of solution, how it compares to how that exothermic process of solvation, how that compares to the endothermic processes of separating the solutes and the solvent particles, that will dictate what the overall delta H of the solution actually is. Now, there's something to consider when it comes to looking at that. Usually, endothermic processes require energy, and they don't happen typically on their own. But in some cases, they do happen. Right? Endothermic process would happen as soon as you mix things together. We need to consider another property of substances, which is something called entropy. And you can think of entropy as a measure of a system, as a measure of how dispersed or spread out the energy is. Okay. Another way to think about entropy, entropy can be thought of as sort of like disorder. We'll put that in quotations. Okay. And the natural tendency for things is to become more disordered as processes occur. Another way of saying that is that there's a natural tendency for the energy of a system to become more dispersed or more spread out as processes take place, right? So for example, if you have two gases here, the yellow gas and the purple gas, and they're separated by a barrier. If you were to remove that barrier, what you would actually find is that those gases will, on their own, right, they will mix together, they will spread out, and they will occupy the entire volume of the combined container, because what that actually does is it increases the entropy of the system. What it does is it spreads out, or it disperses the energy more than if we had them confined to these individual regions, right? So here we say we have low entropy, or another way of saying that is more ordered. And we will talk a lot about entropy and everything involved with it if you stick around and take General Chemistry 2, Chem 15. The natural tendency then, again, is for systems to become, for their entropy to increase. So if we remove that barrier, what's going to happen is these gas particles will mix with each other. And then what that leads to then is an increase in entropy. So we say higher entropy or more disordered. Or more, a better way to describe this would be the energy is dispersed or spread out more here than it does when we have the gases confined to these two separate regions. Okay, so there's a sort of a golden rule that we see in chemistry and also in other disciplines like biology that allow us to determine whether a solution is going to form in the first place. And it's a very simple rule, very simple statement, but we can use it to explain lots of things. And the statement is like dissolves like. And what it means simply is that a solution will form if we have two substances, a solute and a solvent, that have similar type, right? So the like, that's what the like means here, similar type and magnitude of intermolecular forces, right? So in other words, we would expect two things that are both polar, so they both have the same polarity, to dissolve, to be soluble in each other, or two things that are both non-polar in order to be soluble in each other as well. So this is where now your ability to determine the polarity of molecules using your VSEPR theory and electronegativity and all that stuff and geometry to determine the polarity of molecules will allow us to apply this like dissolves like rule to predict the solubility of different solutes and solvents. So a couple of terms that we'll see, if we have two liquids that we're looking at and they're able to be soluble in each other, if they're able to mix them, we say that they're miscible in each other. So for example, we can say that ethanol, which is just regular alcohol, and water are miscible. Right? You can mix them together very easily. Okay, and then the opposite, if you have two liquids that are not soluble in each other, we see that they're immiscible in each other. So for example, oil and water are immiscible, right? They don't mix. They're not soluble in each other. So this actually tells us then, and we can actually do all sorts of experiments, mix two things together and see, or add two things together, see if they mix well to determine the solubilities of things. And if you probably have done this mixture before, ethanol, which is just regular alcohol and water, you know, you stir it up, right? And it looks like one homogeneous solution at the end. We can then predict then that our ethanol, because it's miscible in water, we should know at this point that water is polar. Because ethanol, alcohol mixes with water, we can then predict then that ethanol is also polar, right? Because like dissolves like. If you have a solvent that is polar, then another polar solute should be able to dissolve in it. Similarly, if I compare the oil and water and I see that they don't mix, they're not miscible, well, I know that water is polar. Because the oil doesn't mix with it, I can then predict that even though I don't know what the chemical composition of oil is, I can make a safe prediction that the oil actually is non-polar. Right? So again, it's not rocket science. It's actually very simple. And we can use that rule to predict solubilities, whether things will be able to mix with each other. Another thing that we'll see is that not only do polar solutes dissolve in polar solvents, we can say polar and ionic, as we saw back in the previous sections. These dissolve in polar solvents. And then similarly, non-polar solutes dissolve in non-polar solvents, right? That's another way of stating the like dissolves like rule. Okay, let's take a look at an example or two. So it says, excuse me, determine for each solute whether the solubility will be greater in water, which is polar, or in benzene, which is non-polar. So it tells us that water is polar, which we already know. And I was telling you this thing called benzene is non-polar. Okay, so what we need to do then is to decide if the molecule in question, so a molecular compound, is polar or ionic or non-polar, right? And then we can apply that like dissolves like rule. So if we look at Br2, okay, so Br2, if I draw the structure for Br2, Lewis structure, right? I know that there's one covalent bond here. It's connecting two bromines that have the same electronegativities. So that means their electronegativity difference here is going to be 0. And there's only one bond. That's a non-polar bond. So then this is going to be non-polar, Br2, okay, which means that it will dissolve in a non-polar solvent, which would be benzene. So the C6H6. If we take a look at sodium iodide, NaI, okay, right away we know that this is ionic because there's a metal in it. Okay, so it's made up of ions. Okay, that is as polar as you can get, so that will dissolve in a polar solvent like H2O. Okay, if I take a look at carbon tetrachloride, so carbon tetrachloride actually is down here. So you draw the Lewis structure for it, right? We see that and again, this is an acceptable Lewis structure, but it actually looks like this in 3 dimensions. So carbon surrounded by 3 chlorines in that tetra. Well, we know the CCl bond is polar, but we have 4 of them, and they all cancel out. So the polar bonds cancel. Okay, so which means overall CCl4 is going to be non-polar, and it will also dissolve in a non-polar solvent like benzene. And then the last one here is, what do we have? Formaldehyde, CH2O. You draw the Lewis structure for formaldehyde. Okay, we'll see that it has this Lewis structure. We know the carbon-hydrogen bonds, those are non-polar bonds. The carbon-oxygen bond is a polar bond, very polar bonds. So this overall then is a polar molecule. There is nothing canceling that out, canceling out that dipole. So then this will dissolve in a polar solvent, like H2O, right? So in order to predict whether something will dissolve, you have to make sure that you know what the polarity of that solute is and what the polarity of the solvent is. And if they have the same polarities, they will dissolve. If they have different polarities, they will not dissolve, right? That's like dissolves like.